What is Sierpinski Gasket's link to Pascal's triangle? Imagine a pattern so intricate, it looks like a snowflake made of tiny triangles. Now, what if I told you this pattern is connected to a simple number triangle called Pascal's triangle? That's what we're here to explore. Pascal's triangle is a triangular array where each number is the sum of the two numbers above it. It starts with a 1 at the top, then 2 ones below, then 3 numbers in the next row, and so on. When you look at Pascal's triangle, you see lots of patterns, like the numbers adding up to powers of 2 or binomial coefficients for expanding algebraic expressions. But there's a fascinating link between Pascal's triangle and a famous fractal called the Sierpinski Gasket, which looks like a repeating pattern of triangles inside triangles. Here's how they connect. If you take Pascal's triangle and color all the odd numbers one color and leave the even numbers blank, a pattern begins to emerge. When you do this, the pattern you see looks just like the Sierpinski Gasket. This happens because of something called modular arithmetic, which is a way of looking at numbers based on their remainders when divided by 2. When you look at Pascal's triangle modulo 2, the odd numbers become 1s and the even numbers become 0s. The 0s from the empty spaces and the 1s from the filled parts of the fractal. This pattern repeats itself at every scale, creating the self-similar shape of the Sierpinski Gasket. The reason this works is because the binomial coefficients in Pascal's triangle have a special structure. When you apply the modulo to operation, the pattern of 0s and 1s reveals a recursive, fractal-like design. Each smaller triangle inside the larger one looks just like the whole, which is the key idea behind fractals. This connection isn't just a coincidence. It shows how simple number patterns can create complex, beautiful shapes. In fact, if you change the modulo to other prime numbers, different fractal patterns appear. For example, using 3 instead of 2 reveals a different kind of pattern related to the Sierpinski carpet. This demonstrates how number sequences and their properties can generate a variety of geometric shapes. The Sierpinski gasket itself is made by repeatedly removing the middle triangle from a larger equilateral triangle, leaving a pattern of smaller triangles that look the same no matter how much you zoom in. When you see this fractal in Pascal's triangle, it highlights a deep link between basic mathematics and complex shapes. This connection has practical uses too. In computer graphics, fractals help create realistic natural scenes. In science and physics, understanding these patterns helps analyze complex systems. It also makes learning about numbers more visual and fun, showing how simple math can produce astonishing shapes. So, next time you look at Pascal's triangle, remember that hidden within it is a fractal pattern called the Sierpinski gasket, waiting to be uncovered through a little modular arithmetic. It's a perfect example of how the world of numbers and shapes are more connected than they seem.